good choice. So he is currently in position of Director of Mission Operations for a very important laboratory over in Boulder. Many of you are familiar with LASP, Laboratory for Atmospheric and Space Physics. That's a big undertaking. He will probably share with you some of his experiences with other systems as well, but the LASP laboratory was responsible for at least one very critical instrument on the Cassini mission to Saturn. And I think Bill will be giving you some inside information on what LASP did, some of the challenges they dealt with, and the tremendous success of that mission. So Bill, thanks for coming tonight. Thank you.
Thanks, everybody. Welcome.
Are we missing something Olympics tonight, right? Figure skating? Or, anyways, thanks for coming.
I'm sure we can find someone with a phone to get updates.
No, thank you. No, please don't look at your phone. Fall asleep, but don't look at your phone. Yes, so I'm going to talk a little bit about parts of the Cassini mission, and specifically, not as much about the science part of it, but about the planning, the final few orbits that the Cassini mission had before it was forced to fly itself into the Saturn atmosphere. What I'd like to do a little bit, Jay mentioned that I'm at this Laboratory for Atmospheric and Space Physics. It's a research institute within the University of Colorado Boulder. It's actually started, and the date's probably wrong, it's probably a 1948 start, but we started as the Upper Air Lab, and we were doing experiments, putting experiments on the V2 rockets that we brought over from Germany at the end of World War II. And we were putting instruments that were being launched out of White Sands, New Mexico by the German scientists that were developing eventually the Mercury, Gemini, Apollo missions, Wernher von Braun. We kind of evolved into some of the unique aspects of LASP was we actually in the 50s, mid-50s, we had a couple engineers that kept building the same kind of instruments over and over again, and they thought maybe we should go into production, and they got together with the Ball brothers, the JAR folks, and the JAR folks were looking for another business besides JARs, and they formed Ball Aerospace. So LASP is actually the parents of Ball Aerospace. And an interesting fact is Ball Aerospace, the aerospace part of Ball is the oldest part of Ball because they've sold everything else and they're focusing on cans now. So if you can imagine their board meetings where they're talking about cans versus spacecraft. I don't know how they do that. And then in the 50s, we became LASP. We did a lot more work with NASA, a lot of history, and I'd like to show you a little bit more. Well, yeah, so we have been on lots of missions. I'll show you some more of the missions, but we did a lot of work on planetary missions in the 60s and 70s, and we've expanded that into a lot more, and I'll talk more about that. What's unique about LASP is we're a standalone research institute. We have scientists, we have engineers, we have lots of different facilities where we actually can build and test space instruments. And we have the part that I love the best, because that's what I do, spacecraft operations. We actually operate NASA missions, spacecraft from CU Boulder with undergrad students. So I've got 130 people working for me, 60 of them are students, mostly undergrads. We do payload operations, so you have a spacecraft, you have payloads on there. Some of the spacecraft are operated by NASA, and we operate the payloads that are on those spacecraft in a separate facility. We bring that data down, we do scheduling of what we want to do with the satellites and the instruments. We bring that back to the scientists, and when the scientists say, wow, I didn't expect to see that, you know it's cool science. But we do that. We have about 600 people working at LASP. They're university employees, but we're totally funded by NASA or National Science Foundation or commercial. We do some commercial work. And we're actually doing a project with United Arab Emirates, the UAE. We're collaborating with them on a mission to Mars. So in 2020, we're building a spacecraft now. We're building the instruments with them in Boulder. We're going to ship the spacecraft to Dubai for some final testing. They're going to ship the spacecraft finished to Japan for launch. And we're going to have a backup ground station at Boulder, and the primary one will be in Dubai. And it's celebrating the 50th anniversary of their country. And so if you know the area, they're in a rough neighborhood, and I think they're trying to show their young people there's a different path. You can go down the science technology path as opposed to another path. So, and it's interesting, the head scientist for that mission is a woman. So they're a little bit more progressive in some areas. Our history goes back, as I said, to the 50s, but in the 60s and 70s, if you look here, we've covered every planet in the solar system with different missions. We've studied the Earth, we've studied the sun a lot, and it's probably hard to tell, but we have gone to every planet in the solar system. We have built an instrument that's gone to every planet in the solar system. Nobody outside of Mother NASA can say they've done that. There's no other institute, even within NASA, that's gone to every planet in the solar system. And we're operating the Kepler spacecraft. If you're familiar with Kepler, Kepler is the one that's finding thousands of planets, 4,000 some planets. And we've, pretty much with Kepler figured that if you look at the stars at night, about every other star will have planets going around it. And about 1 out of 10 will have an Earth-like planet going around it. And if you count the stars in the galaxy of 100 billion, and you say 10% have Earth-like planets, it sounds like a lot of planets, a lot of Earth-like planets. So the Cassini mission, very special for me. Jay mentioned I worked on launch vehicles for a little bit. When I was still Air Force, I worked on the Cassini rocket, the Titan IV, that was built in Denver, Waterton, by Lockheed. The spacecraft was built by the Jet Propulsion Lab in Pasadena, and LASP had built one of the instruments that flew on Cassini, and I'll talk a little bit more about that. It was an ultraviolet spectrograph. And the scientist that actually worked on that developed that instrument, was a graduate student on Voyager. So he worked with Carl Sagan, if you're old enough to remember Billions and Billions. They still, and as a graduate student, he discovered one of the dimmer outer rings of Saturn that they picked up in photographs as Voyager flew by Saturn. So, and he's still around. But the Cassini mission had several different phases. So it arrived in 2004. It has what they call the prime mission, and that's where you do your primary mission, and if everything goes well and the funding keeps going, you can do extended missions. And then we had an equinox mission and then the solstice mission. They knew eventually that we would have to finish the mission of Cassini, that there's some fuel on board that it was running out of, and we didn't want Cassini to just fly by itself and eventually hit one of the moons of Saturn. So it was an intentional, let's bring it down into the Saturn atmosphere. And I'll talk more about why we wanted to do that. Cassini's a big spacecraft. Titan IV was the largest rocket we had in the 90s. It's 20-some feet high, 13 feet wide. But the funny part is, you look at the recorder, half a gigabyte, by today's standards is pretty small, but in the 90s it was big. And it also had this European probe on called the Huygens probe, and that's the one that had a parachute on there, and it actually did a somewhat soft landing on the moon Titan, and it got to look at these methane oceans that are on Titan. It was launched in the Titan IV, and we love acronyms in NASA. The trajectory, VVEJGA. Anybody want to guess what that is? Yes, no. Venus, Venus, Earth, Jupiter, gravity assist. So to get to Jupiter, it was not a direct route. One of the interesting things is New Horizons, the mission that went to Pluto, was a very small spacecraft launched on an Atlas V, big rocket, and it was direct. It just took off and shot. This guy was so big, we couldn't do it that way. So it went, the slingshot maneuvers, went twice around Venus, came back around Earth, and then swung itself out to Saturn, flying by Jupiter at the same time. Very tricky. The launch window, we had to have it was a very tight launch window. And there's plutonium fuel on board the Cassini spacecraft. So it's radioactive, small amount. There were some interesting dynamics here with some environmentalists. This was launched out of Cape Canaveral, again, the Titan IV. And this launch window was a couple days open, so that we had to launch it during that time. There was a group that was concerned. We have an Earth flyby here, and the concern was, what if you crashed into the Earth with this little bit of plutonium? So they filed an injunction at a court in Honolulu the day before launch, and the program directors had to fly to Hawaii to go before the judge saying, we're safe, here's the documentation, we've done the analysis, and then they flew back to Cape Canaveral for the launch. So it worked out fine, and everything worked out fine. We were sweating. Saturn system, lots of really small, cool moons. Obviously, you've got some beautiful rings. You know, it's one of these, hopefully you've looked at Saturn through a telescope. It's one of the most fascinating, beautiful things, even in a small telescope, to see. And you know, when you go out to have public star parties and you have a little kid that looks through the telescope and sees Saturn, and you get the wow factor, it's very pretty. And then, so we had different missions that went by these moons, and Cassini was obviously the one that studied the most. And how do we get the name? Cassini Huygens was an astronomer, Dutch, looked at the rings, and then Cassini was the one that actually discovered several of the rings and of the moons. Italian guy. So the mission, if you look at the different years and what we flew by, we wanted to study some really interesting things. Titan was a big one because we knew it had an ocean. It happened to be methane, which is nasty, but it was still an ocean. We didn't know much more about some of these other moons, and so we focused the first few years on lots of Titan flybys and studied the atmosphere of Titan. And then we started doing more of other moons, flying by them in different seasons. So we did several orbits each year, but we tried to cover lots of different seasons. And then out here on the very right, on the 2017, is when we came closer and closer and closer to the planet. And that's what we're going to talk about tonight. These orbits, the planning that went into it, the execution, the dangers that it went through to collect that science. So Cassini, the tour, here's your planet. That's how many orbits we did. That's a lot. Actually, it looked more like this. So different times, different orbits, these are all the different orbits we did over the years. The solstice ones here. And then we had added some more to the outer. We started looking at the outer rings. And then we added the last few to look at the inner rings, to look at flying through the rings, between the planet and the rings. So focusing on that. And if you look closely, there's an orange pass here, which was the final pass before it went into the atmosphere of Saturn. So they called this blue part the grand finale. The outer part you can see here, we're just grazing the outer part of the ring. Here we're actually flying between the planet and the rings. Some tricky flying here. So the objectives. The idea was to get Cassini cool science, but end the mission. Planetary protection is a really big deal. We worry about that a lot on our Mars missions, and we pretty much have to, sterilize as much as we can because you're concerned just in case something from Earth, microbes, would go to these outer planets and contaminate it. So we take a lot of care decontaminating things, but when we can, we want the spacecraft to completely burn up and not hit the surface. And at the same time, we wanted to do unique science. Measure the internal structure of Saturn, the ring mass, how much mass is out there in the rings, what's the age of the rings, and then getting some really close-in measurements of the ionosphere, radiation belts, the auroras, and that's something, the auroras of Saturn are pretty spectacular, has a huge magnetic field, and our instrument, the Ultraviolet Spectrograph that we had, was one that could make movies of these auroras. And of course, cool high-resolution pictures. They call it the proximal orbits and proximal environment. So here's your planet, here are the orbits. You can barely see the orange where it goes into the planet. So what's the environment like? Here's a high-resolution black and white photo. You can take that and you can overlay where the rings, the plane of the rings, and where you are through this orbit, through these different orbits. And these are called the ring crossings, ring plane crossings. And that's where, the majority of your ring particles is going to be through here. And you've heard of perigee. So if it's on a planet that's different than Earth, you call it a periapsis. So this is the closest point for each orbit, the closest point where you are to Saturn, periapsis. Now you lay that out there, and here's the ring crossing and periapsis. Or the other way around. So you throw that in there with this proximal corridor. And what you're trying to do is understand what that spacecraft's going to go through and what do you have to do to protect it. So here, this is the distance from the center of Saturn. When you are closest to the planet, you're going to get an atmosphere and it's going to torque. It's going to jerk that spacecraft a little bit. Down here is the spacecraft capture boundary. So when you get down here, there's no way Cassini's going to survive. It's going to re-enter. And you want that to be on the last day. So these were the orbits that they were planning to do. And this was over a several month period, August to September. So what do you have to deal with on the environment? Dust from the rings and the atmosphere of Saturn. We have shields. Beam me up, Scotty. Shields on. No, we don't. But we wish we did. So, but you do have something like shields. So the main engine has a cover, and it expands. So you can close the main engine assembly. You have this beautiful high gain antenna. This is the antenna that communicates with the Earth. It sends the data back to the Earth that you're collecting. So when you turn it to the Earth, you're basically not doing as much science as you could be doing because you're transmitting data. But you can put that as a shield. You can put that in front of your dust if you're concerned about it. You're just not going to get too much science, but they knew that this antenna, the high gain antenna, was the most solid part of the spacecraft and could withstand some of the dust. The atmosphere. So when you get close to the atmosphere, you can turn on your thrusters. You can fire thrusters and get yourself back in the right position. You also can do this torque attitude maneuver. and try to position yourself so you're not being dragged in as much as you would normally. So how do we do this environmental hazard protection? So if you're going to try to protect yourself from the dust, you have to have some time to put that shield in the right spot, and that time is right through here, and then the max torque is right over here, or the minimum. To minimize the torque is over here. But you need time to do that. You need time for turning, so that part of the orbit, you're not going to be doing much science. That part of the orbit, you're not doing much science. But that's really where the scientists want to go. So how do you know what that atmosphere is like? So there's a way to measure the atmosphere, distance from the planet. There's our boundary here. And so we figured this was about the place where if you were below this, you couldn't really fire enough thrusters. You were concerned that the thrusters wouldn't work well enough to keep you alive. So they figured these orbits here are where you're going to be putting the thrusters on and using reaction wheels. These are wheels that kind of keep you pointed. So we're throwing all this stuff in there, trying to figure out where we are in order to collect the science and keep us safe. So how do we know where the dust is? So we kind of look at this photograph, and you can look at the brightness coming through there and actually measure it. So you look at the brightness and where you are from the planet, and the main area that you're worried about is down here. So even though it looks the brightness is pretty bright compared to up here, that's where the area where you worry about. So this is if you imagine the planet's down here, this is the D ring. So that's the other ring, and we're flying between the D ring and the planet. So with the D ring and the dust, you're kind of worried about that area up here. So that's the area where you're kind of worried that if my measurements are right, I've got to take extra caution in these different orbits because I'm so close. So you've got passages now with the high gain as a shield where the X is, and so now I've got to turn that high gain antenna towards those rings, that D ring, protect me from dust hitting the spacecraft. And if you know about the rings are actually dust and mainly ice particles. So one of the scientists and the engineers, the debate they always have was, how close do you want to get to the dust? And how close do you, because you're basically taking your spacecraft and driving through a hailstorm. And spacecraft weren't designed to drive through hailstorms because it's that, if you read about something, the other thing that Cassini found was on one of the moons of Saturn called Enceladus, it actually has geysers. So it turns out it's a moon very close to the rings, and when they flew by it, they saw these took pictures, and there was these huge plumes, kind of like Old Faithful at Yellowstone, except the plumes are not caused by heat from the moon. It's actually gravity. The force of gravity is heating water, and it breaks through ice and shoots a geyser towards the rings of Saturn. And we flew Cassini within 12 miles of the surface to get better pictures of those geysers. But now they know that there's, potentially warm water because it's being heated by the gravity of Saturn somewhere underneath those geysers. And usually the scientists kind of say if there's water, there could be life. They're planning missions out to Enceladus now. Once we get through Europa on Jupiter, we're going to head towards Enceladus. Anyways, back to this. So we're struggling trying to find ways to protect ourselves. We're doing it with the shields here. How do we measure the different the dust? We've got a dust analyzer, and dust makes a plasma wave. We can hear it through this plasma wave sensor. When it comes to the atmosphere, Cassini's a smart spacecraft. It wants to save itself. It has thrusters, and since it takes many minutes to communicate because of the speed of light and the distance away, it's not like you can sit there and hit it real time. So it has an onboard computer, onboard attitude control system. It can sense when the atmosphere is pulling on it. So it will, on its own, fire thrusters to keep it alive, keep it safe. And you can see those thrusters firing because there's dust hitting it. So back to our little description here. So this is the one that, the first orbit is the one that we're kind of concerned about. We want to make sure that we are measuring things properly, and we have a way of doing that through the detecting of thrusters firing, the plasma detector, and the cosmic analyzer, cosmic dust analyzer. So yeah, so we're going to take a look at these orbits and make sure that we're doing these correctly. So the way they did that was they want to take this first orbit here, and before they go into this orbit, they want to make sure that the analysis they did previously, the dust, make sure they're safe, that they do things right, and then if they need to, make a correction on the next orbit before here. And the way they did that is, here's that orbit, and this is the one that the first ring crossing, and this is going to be the second ring crossing, and this is the orbit that it's going in. And the way we communicate with Cassini is through the NASA Deep Space Network. It's a series of large antennas, 70 meters. They have ones in Goldstone, California, Canberra, Australia, and Madrid, Spain. So they're global. And they use these antennas to send the commands and collect the data from Cassini. But there's only so many times when we can actually see the Cassini spacecraft and communicate with it. So you're flying around here, and here's the first contact. So we're 5 days away from, we're 1 day into from that collection, and now we bring that data down. We're analyzing this dust data based on the instruments and the thrusters, and we have 5 days to do the analysis. Sounds like a lot. I think it was very complicated stuff that they're collecting, and I'm sure they went into a lot of detail with it. But they put in some contingency passes. So if we had, this was the prime one. If we did the analysis incorrectly and had to make a change, this is where we would be sending commands to Cassini to say, stay with your shields up and your thrusters firing. But we also put in another one just in case, where we were 1 day out and 5 days away. So in case something happens, these antennas are, they're mechanical. So things go wrong. Sometimes you don't get your pass correct. The gears lock up, stuff happens. It rains in Spain, and you can't get your signal through. It's true. Raining in Spain is bad for the frequency they use to communicate with it. So they had another contingency planned. So then you can figure out, you could go through it. Turns out we were good. We didn't need to do any more than that one pass. The analysis that they had done was correct. So we did not have to do any more shielding. We went ahead and collected our normal science through those. Okay, so grand finale. These were the orbits through here. First one, terrifying. You can imagine, did I do my analysis right? Did I do my, did I put a plus sign where I should have had a minus sign in my analysis? Did my software work correctly? So a lot of sweat went into that one. But, it was successful, and we completed all the orbits. So again, just a summary here of how we did that. The idea was to do the disposal and worry about the hazards. Contingency plans, with measuring things, and real-time, in a way, reaction if you had to do it differently. Okay, so I'm going to talk now about the science that what they want to do and the science planning. Maybe not, I'm not going to talk so much about the results, but more of, here you have all these different instruments, and you can imagine with every one of these instruments, there's a crazy scientist behind it who says, this is the most important science you're ever going to collect on Cassini. True, they're all that way. They're very passionate people. If they've been on Cassini the whole time, they probably started this in the early 90s in the planning. And here it's 2017. So they've lived with it almost their whole career. So here's all the different instruments and the kind of things that they can do. There's an optical part where you have the cameras and imaging. You got microwaves you're measuring, and the magnetic field and the plasma science. This is it's small, but it was important, the Ultraviolet Imaging Spectrograph telescope that CU LASP built is in that area here. Doesn't look like much, but it's about the size of a, I don't know, you're a little bit bigger than your milk container that you put outside, or your cooler that you carry. So again, the things we wanted to do, the science we wanted to do, but at the same time you had to kind of worry about planning for it. What could you do? What is the most important science? When could you do it through this planning process? They actually started back in 2013 planning for 2017 passes. This is at the same time that they're planning the current missions. So there was a different group, but they have a very well-ordered process. They look at which is highest priority, how do you integrate everything, and oh, by the way, there's pointing involved, there's power involved. Some instruments take more power, some take less, but you can't do everything, you can't please everybody all the time, and you can't please all scientists all the time. And then you have to look at how you create this into commands and execute these. Execute meaning perform, not kill. So it doesn't look bad, but you throw a few more things in here, like sharks in the water. If you see the little shark there, there's always sharks in the water. It gets more complicated than that. So you're also executing the current sequences, so the 2013, 2014 science has to get done. So the way they decided to do, when there's sharks in the water too, yes. So you wanted to start planning this well ahead of when we had to do it. And you wanted to look at the closest approaches. Again, the scientists were just, anxious to have this close proximity pass. At the same time, the spacecraft engineers were kind of saying, but I want to be careful. I want to be careful. I don't want my spacecraft to, get smashed up by this dust particles. So you balance that out. So we throw that in there. And so let's look at the different instruments and what science is done with each one. The antenna, the magnetometer, the in situ measurement, the magnetics stuff there, plasmas, different instruments. I won't go through all the acronyms, but there's lots of instruments that wanted to do different types of science. And a little more challenging. Again, each one of these has a mad scientist behind it. The geometry of the spacecraft, the way they were planning to fly, was looking at this way. High gain antenna was pointing towards the planet. So that was an important part. And how many passes do you need to get the science that you wanted to do? So one group wanted 6 passes, 2 or 4. All these other guys, 8, 3, 2. They all needed different passes, number of passes. And when you add those up, 36 passes, but you only have 22. You can't do it all. You can't do it all. So what do? Just like in kindergarten, you say share. Sometimes you have to treat these scientists like kindergarten kids and tell them to be nice and play with your toys and share your toys. So what do? We put them in a room. We made a working group out of this. You get the guys in a room and you say, work together. Let's get this done. Let's get it worked out. Each one had their own pointing requirements and kind of just different ways of pointing, different science parts of it. They were concerned about the temperatures of the instruments, hot, cold, and so they kind of laid out what they needed to do for each one. Then they kind of grouped them into the different orbits. These are the, you probably can't see that. These are the different orbits where it works out for them. And then they look at where they can go and do things with multiple instruments, and everybody's happy on those multiple instruments. So they kind of, they kind of laid out everything by this process. They look at the power, what they can share, make sure they can do it all. We did have some, you worry about unexpected pointing uncertainty. Am I pointing the right way? Is my pointing design proper? They call dual playback. Sometimes when we have these antennas, you play it back, that you send the data, and it doesn't come through completely. And you want to play it again because you don't want it erased off your recorder. So if it's really important, they'll play it back twice, which takes time away from other instruments to send their data. But it was important enough that they had requests from the scientists that they wanted it played back twice. The execution phase, this is where you're planning your 22 orbits. You look at constraints, you look at where your commands, your schedules. Again, there are lots of uncertainties going involved in that, and end of mission kind of things. How much science can you get real time before the very end of the mission? So you throw that together, and there were 18 segments delivered January of 17 when the program was going to end in September of 17, but you were starting that phase in April. So they actually did a very good job of getting this cranked out for several years. The science continues to be analyzed, and it's going to be analyzed for years. We finished the mission in September, but they're still going through data now. There'll be papers published for years to come. You're starting to see more of the high-resolution pictures come out. If you go on the NASA Cassini website, they've got some really cool, very high-resolution pictures. Some of these are pretty phenomenal. You can't actually see the grains within the resolution is not that good that you can see individual, boulders in the rings. They're still too small, but it still has fantastic results. So the timeline, we did the grazing orbits in 2016. That's kind of what it looked like. In 2017, we started the final flyby of Titan. So we go down there, swing across. 23, we started the final finale orbits. First one through the gap, as I mentioned, was the one that was concerning. Then we kept doing more and more. It's very successful. And then 2017 was the last time we flew by Titan, but it was intended to throw us into the atmosphere. And it did. Final impact. If you look at, I think there's an animation somewhere, I didn't have it in here, but when they looked at the data, the last bits of data coming from Cassini. We intentionally wanted to put it in the atmosphere. It tried like crazy, firing thrusters to keep it alive. I mean, it was firing left and right, and then finally, no data. I know, but I know. Okay, let's talk about the wonderful part of Cassini. Saying goodbye, say goodbye. And this is a little cartoon, this is cute. So Cassini, I hear you're retiring September 2017, congrats. How do you want to celebrate? Maybe do lunch with me and all my moons or something? Nah, I'll just go barreling straight into your atmosphere, learning as much as I can before I'm crushed to death and vaporized in a spectacular whirling inferno beneath your mysterious stormy clouds. That's awesome. It's a biologist who did this. And she is a scientist. Just happens to draw well. Some cool images, the rings, when the moons, the detail in the rings, pretty spectacular camera for a 1990s version.
What was happening in the upper right there? You see shaded bands or something?
Here?
The wavering?
Where?
Okay. Anything special about that picture?
Just the detail. I'm not sure if there is any more. No, just the detail. This is kind of a cool animation. Imagining you're on Cassini, flying through the rings. Oh. Nobody gets sick, right? Uh-oh. Something stuck?
The PC's from the 90s too.
Yeah. Okay.
It must have hurt your comments about that.
I know. Is there a way to get out of it? F5? Yeah. Okay. Control Alt Delete.
Did you say what the passing velocity was for the?
Oh. No, I know they've calculated it. Yeah, I'm not sure. It was pretty fast, obviously. But. Do you want to? Should I skip the animation?
He's got to try it.
Okay. Okay. I think it does it several times. So if you weren't sick the first time.
Is that
Yeah.
sped up or is that actual?
No, it's days, right? Yeah, it's sped up.
That was Cassini, the ghost of Cassini.
The ghost of Cassini?
On a crash.
Right, right. Okay, and then JPL. This was at 5 in the morning. JPL had a, kind of a celebration in Pasadena Jet Propulsion Lab because that's where they operate the spacecraft, and a lot of the scientists were there. LASP had an event. What was interesting is we initially wanted to do just the LASP members because who would show up from the public at 5 in the morning for something that really was on TV or on the NASA network. And so it turns out we had 150 people show up at, and all the different news channels from Denver showed up too, 5 in the morning. So wanted to play you several news clips came out of it. The most interesting one was from the American channel that does the China news. And so if you can turn the sound up.
Say goodbye. I'm at JPL, the University of Colorado's Laboratory for Atmospheric and Space Space Physics, or LASP, and at Mission Control in California, it was a bittersweet occasion.
The excitement is really palpable.
That's Larry Esposito, who built the instrument.
And half a dozen boxes of Kleenex.
And liftoff of the Cassini spacecraft on a 30-mile trek to Saturn.
The Cassini spacecraft blasted off nearly 2 decades ago and began orbiting Saturn in 2004. Its dozen instruments spent the next 13 years trained on all aspects of this large and mysterious planet.
The Cassini mission is huge.
Fran Bagnall analyzed data from LASP's Ultraviolet Spectrograph, a remote sensing instrument which studied Saturn's atmospheric composition.
The biggest discovery was the moon and Enceladus had volcanic vents of water coming jetting out.
An indication that primitive life forms might just exist there. As with all vehicles, Cassini was on the verge of running out of fuel. It could have continued to orbit Saturn on its own, but engineers didn't want to risk having the spacecraft crash into one of its moons, thereby potentially contaminating that moon with the Earth's bacteria. So after 5 months of diving between Saturn and its rings, Cassini was plunged into the planet's atmosphere, where it disintegrated.
So I lost the signal at 115546. That would be the end of the spacecraft.
A mission that's provided over 635 gigabytes of science data already.
We're going to continue to analyze this data for years to come and continue to...
Sorry, I had a tie.
Complex data than anyone realized, Bagnall says, one that could be key to comprehending our role in the universe.
To understand how we here are on Earth, we need to really understand the whole system of the solar system.
This Warrior spacecraft helped shape that understanding. As one scientist put it,
It perseveres, it's done everything that we've asked it to do, and more.
Cassini completed almost 300 orbits and traveled almost 8 billion kilometers to get the job done. Hendrik Sabrandi, CGTN, Boulder, Colorado.
Cool. Okay. Yeah, we don't want the next one. Turn it off, turn it off.
Facial recognition technology has existed since the 1960s. However,
Okay. Anyways, thank you. I'm happy to take any questions you might have.
Do we know what happened at the end? Was it tumbling, or was it in a certain
It was
orientation?
supposed to be in an orientation, and as it got closer, it started firing its thrusters to stay in that orientation. Yeah, and then it just plunged in. But it was seconds, basically. Yes?
The slide that you had that had the contingencies on there, the dates, got me thinking about how far away from Earth is Saturn, and how long did those signals back and forth? It sounded like there were signals like back and forth.
Yeah, it's about a half hour each way. So you weren't going to do it real time. You had to send the commands, they get stored, and then there's a clock on board Cassini that says, do this at this time. So that's why they had to do it so far in advance, trying to make sure it got into the computer to do it when it was supposed to. Yeah. Yes?
So designed in the 90s, what was the processor technology that was flown?
Oh, I don't know.
You suppose it was like Cosmac, RCA, because they had really good rad hard and stuff.
It had to be pretty good rad hard. It was you know, Cassini was one of the most expensive missions also that we put up until James Webb is going to be the most expensive. But Cassini was, you know, it probably was pushing $1 billion back in the 90s, which was a lot. But I don't know what was on there with the processor.
I think it's 386.
386?
I had a little bit.
Okay.
I worked at NOAA at that time. I remember they were just certifying the 386 for spaceflight in like 91 or 92.
Okay.
So I imagine that's probably what went on Cassini.
Okay. Yeah. Yes?
What language was used to communicate with the satellite? Like, was it a computer language, or was it?
Yes. Well, I mean, you basically send ones and zeros. So the commands are a string of ones and zeros that is a, you know, there's a, They call it a command and data handbook. Every command has a certain format that you send it. And so it's pretty standard format for a spacecraft to communicate that way. Yeah?
Bill, I heard there was fuel loss with Cassini. Was the original in the planning process, was it to always impact the planet, or was it to bring Cassini back?
No, it was always to impact. Yeah. It was a matter of when, not if. And so every few years, Cassini had to go to NASA and say, here's the great science that we're getting with it. We would like to continue the mission, and we would like funding for it. And so every year they kept getting the funding for it. And so really it went well beyond. As he said, everything kept working well. And that's one of the factors that NASA looks at. Are your instruments still working properly? Is there worthwhile science that can still be done? As Professor Bagnall said, the Enceladus just blew people away. I mean, that was the biggest discovery we had with Cassini, and lots of other discoveries, but finding liquid water on a moon is pretty wild. Yeah. Yes, in the back.
What kind of computers did they use to compute? Obviously, they didn't do everything on paper.
Right. Yeah. I'm not familiar exactly what computer they used on our IUVS instrument at LASP, but we had a problem in that was the last computer, and if it failed, we didn't have another one. That it was going to be going on eBay and find the antique store. Yeah, that actually, for these missions that last a long time, that's one of the problems, is keeping the hardware and the software, because you basically freeze the software that's in there. And so it was 1990s software that was in there and the 1990s computer. So, yeah. Yes?
Yeah, so on Cassini, there's all these instruments.
Yeah.
And as you were saying, there's like separate scientists who are like, believe that like this is the thing. Are those people, are they like invited, like, hey, I hear you're cooking up some cool instrument. Do you want to have it on our spaceship? Or is it more of different groups come to like, oh, we've heard you're putting something in space and we want it in space?
Yeah, it goes both ways. So the reason we had the spectrograph on ours at Ultraviolet was because Larry Esposito, the guy with the white beard who was at JPL, that's his science, and it was such an important science that they came to us, Larry in our lab, saying, we want you. We want you to fly on there. Other times, you're at a science conference and you hear somebody's instrument and you talk about your science, and they kind of come together. So a lot of it is through these science conferences and papers that people publish and getting to know the scientists. So there's collaboration, there's competition, and then there's there's all sorts of ranges of that too.
Lots of proposals being written.
Yeah.
And that's the boring part about the whole thing, is if you have a cool science or something that you want to be investigated, you got to write proposals and send things out and go bang on doors and everything else to see what spacecraft you can get a ride on too sometimes.
Right.
So it's not just,
yeah.
hey, what's available? What can you find?
One of the things that Kepler found all these planets. The scientist wrote his first paper in 1980 talking about how to find planets with the method that Kepler was using. He was, 3 or 4 times the proposal was turned down. He finally got it funded. Then it was overrun. Then they were threatening to cancel it because it's overrun. And then, finally got it launched, and look at all the science that's come out of Kepler. And it was that close to being canceled. And again, the scientists spent from 1980 to 2007 to see his spacecraft go up. And lots of rejected proposals, and he kept writing more proposals. So, yes?
I got another question concerning the mathematics that's involved in it. I worked with a mathematician quite a few years ago, and he made a comment to me one time. He says virtually anything in the universe can be figured out mathematically.
Okay.
And I have to kind of agree with him. But what level of, or what types of mathematics, maybe for some of the younger people here, are used? I don't know if you can address that or not. In figuring out the orbits and things, that blows my mind.
It is. It does.
You get gravitational forces and all that.
Yep. And, you know, all the different moons and the gravity of Saturn and the uncertainty of things. And what blows me away, and I'm only a physicist, not a mathematician, but flying over a moon 12 miles from the surface with your spacecraft. Just how do you do that? And
Did they have to actuate any of the rockets on there, you know, for the thrusters and stuff to compensate for the
yes.
mass of that?
Yeah. I mentioned, I kind of glossed over, it has reaction wheels. So reaction wheels are big wheels on the spacecraft in 3 axes that are spinning, and you can basically keep something pointed in the same direction with these spinning wheels. If it doesn't point accurately enough, or you fire the thrusters. So thrusters are kind of a last resort.
Are those spinning all the time, or are
Yes.
they just spun up?
They had 4 reaction wheels, 1 failed, 3 were working still at the end. You need 3 to point it properly. So, yeah. Yes?
So you were talking about the size of the instrument that LASP built?
Yeah.
And you said it was like the size of like a
Cooler, yeah.
How big is Cassini?
School bus. Yeah. Yeah. It's big. Yes. Yeah.
I just had a question, because now you got a couple decades to look backwards at it. Do you think that all the solar system research and science type missions are going to be NASA and Institute kind of based, and all the manned space flight is going to transition towards the private sector and the private public?
It's looking that way, isn't it? It's kind of moving that direction. You know, it's interesting, you know, the president's budget came out, and, you know, he's putting a lot of money, they want to put a lot of money into human flight as opposed to Earth science, but they're also putting more money into going to the moon again. But you know, Elon Musk wants to get there sooner, and he's got the money to do it. And you know, so and he's got the.
Tell somebody how many instruments that we got on that farm.
I know. You know, and okay. You know, how many scientists would have loved to put their instrument on that rocket that's going out there and doing science, as opposed to sending your $250,000 car into space? But the publicity he got was phenomenal, right? You know, and so it gets people more excited about science and space. So there's a trade-off here, right? Interesting thing is, you know, you've seen the really cool pictures of Mars from spacecraft. You know, there's several Mars orbiters up there. The rovers have cameras. We did a mission called Maven, and I've got a brochure on that in the back. It's orbiting Mars. It's looking at where the water went. It's looking at the escape of water from the atmosphere into space. No cameras on there. And so the head scientist is at LASP. He's one of our senior people. And, you know, having talks with him about, why not just put a little camera on there? Why not, you know, that's the first satellite to Mars that didn't have a camera on board, a visible camera. He goes, but there's no science value in that. You know, he wanted everything on instruments. So he won. I lost. He didn't put a camera on there. But yeah, interesting.
Bill,
Okay,
can you
yes,
stay around for a few minutes for an individual question?
Sure,
Just one more
yes.
thing.
How long do you expect Cassini to live before it crashed?
Good question. I think we were at the max number of years. So I think we were close to the, you know, thinking it could end at any moment, and we better do it ourselves. You know, if it lost one more reaction wheel, it would have been, you know, very little science. Here was a chance to take this beautiful spacecraft, still working really well, get really cool science, and then end the mission. So it's pretty close to the end. Okay, thank you very much. Appreciate it. Thanks. Sure. Yeah.